Hello Python programmers, let's talk about pandas. Not these pandas. They are cute and cuddly and they like bamboo, but they probably wouldn't be much help writing Python code. This is our pandas. We are going to import two libraries, pandas and numpy, because they go together. I will be building a Jupyter Lab notebook as we go through this discussion. And I like to group my import statements at the top in their own cell. I only have to run that cell once unless I go back and add another import. So that makes me a little more efficient and the program runs a little bit faster. First, let's look at the concept of a series. It's somewhat analogous to a NumPy array, but we can give it an index rather than just indexing numerically. We can literally give the individual elements index names. And theoretically, or on the surface, the series can have different types of data in it, but it doesn't really work out that way. I'll show you that in a bit. Here's some example code. In this example, we are creating a series from a NumPy array. You can see NumPy coming into play here. The elements in this array are A, B, C, D, E, and the word cat, all in quotes, meaning they're strings, or Python generically refers to those as objects. The last element in that NumPy array is an integer 42. So we take that NumPy array and we pass it to pd.series. PD is pandas. Series is a class, and that is actually a call to the class constructor. We don't talk about object-oriented programming in this class very much at all, but behind the scenes, that's a call to a constructor. We pass to that series constructor the NumPy array, and then what we get back when we do that assignment statement is our series. We'll run that code in our notebook. Notice that when I print the series, just using the print statement, it gives me a numeric index on the left, which we can override, and it tells me the data type of that column is object. And the reason for that is because at least one of the elements in that NumPy array is an object. I emphasize data types as always because the data type of a thing, a variable, a constant, a column, a series, defines what you can do to that thing. If you'd like to perform math on something, it better be a numeric type, or you better be able to convert it to a numeric type on the fly as necessary. So in this case, since A, B, C, D, E, and cat are all strings, they're all initialized with quotes, it doesn't matter what the 42 is because NumPy or Pandas has decided that everything will be an object. Actually, NumPy decided before it got to Pandas. If I have my heart set on doing math, then I'm going to create another NumPy array. My NumPy array is 1, 2, 3, 4, 5, 42 minus 100. All of those are integers. They have no decimal places. They have no decimal point. They're within the range of a Python integer. And then I can create another series. My series 1 equals PD dot series my data 1, print that out. That's going to be a data type of int 32 because Python NumPy analyzed the contents of that initializing data set and realized that all of them would fit nicely into 32-bit integers. Now if I do the same thing, and let's make one of them a floating point number. So I'm going to go back and edit that my data 1 NumPy array, and I'm just going to put 100.5 is the very last initializer. So now we've got a situation where all but one of them are integers, and this is not a case of majority rules. This is a case of adapting to whatever's necessary to store that data. And they all have to be the same. It's homogeneous. Therefore, we get float 64 as the data type for that series when we run that little snippet of code. So when you store something in a NumPy array and then convert it to a series, be careful, because if one of them is a string, then they will all be strings. I mean, it looks like a number, but when it prints out, it's actually a string behind the scenes. I'm going to comment out these. Actually, I guess I will. I'll comment out these extra 3 lines that I added. I'm just trying to keep my output from getting too cluttered in this notebook. And of course, I could just delete the output by saying clear outputs. And the cell persists, but the output of the cell is no longer visible. So we were able to create a series. We did not provide an index, therefore we got numeric index values from 0, indexing by 1. But if we decide we want a more useful or engaging index, we can provide that when we reference the series constructor. In this case, I'm defining an index as one of the arguments, and I am using the keyword argument index. So that's a reserved keyword that the series constructor recognizes. And if you use that keyword index as an argument to the series constructor, it realizes that it should override the numeric indexes it would create by default and replace them with whatever is in that index argument. In this case, I provided a list. And since a list is iterable, it simply iterates over that list and assigns each row in that series that index. Also notice that the data type of this series is float64 because all the initializers in the NumPy array are float64. And let's see if we can break this. It's not too hard actually. Let's add another value to the NumPy array. What is Amazon stock? I have no idea these days. 5,000, 3,000, something huge. So now I have 5 initializers when I create the NumPy array, but I only have 4 index values. Let's find out what Pandas does with that. As expected, that blows up. The error is okay, I guess. Length of passed value is 5. Index implies 4. And if you take a close look at that line of code where the error took place, you can see that there is something in there called an index. That's that keyword argument. And there are only 4 things in that list IBM, P&G, Microsoft, and Home Depot. But then when it actually tries to create the series in the following line of code, in that line of code, it compares the number of index elements with the number of data elements in the NumPy array, and they don't match. And that's why you get that error message. And you have to go back and fix that. You could add another index if you like. That should fix it. This adds another row to the series. The series still consists of one column with unique index values provided. Slide 7. We can do neat things with the index, even though it's a string, even though it's the stock or the name of the company, not the stock symbol. We can use that as an index into our series. And this is extensible. We can use that as an index into a data frame too. In this code, we're doing it two different ways. In the first example, we're going to call, or sorry, not call. We're going to index using square brackets, using the symbolic name of that index, IBM. Again, it's in quotes because it is a string. And then in the second, we're going to use two indices. Both of them are wrapped in square brackets, but the second one is wrapped in another set of square brackets, meaning that's a list. So we're using a list as our index into the series. Don't see that very often in other languages. Anything that's iterable, anything that Python knows how to step through one element at a time, can be used in that context of an index. Again, the first set of square brackets means index notation. The second set of square brackets nested in there means an iterable object, in this case a list, of individual index values. And I typed it wrong, didn't I? Oh, the quotes are wrong. I am so sorry. They don't come off the slide correctly sometimes, do they? Got some quote fixing to do. Let's try it now. Fixed all my quotes. There it is. The first print statement prints 134.29 because I only provided one index, so there's no need to specify anything else. The second print statement prints the index and the column value, because since there are two of them, it's important to be able to differentiate between them. And out of curiosity, let's see what data type this is. I'll bet you can guess. So if I do a print on type, my series, and I did something else wrong. Oh, I need another paren, sorry. The value returned by that indexing operation is in itself a series. Indexing into a series using multiple indexes returns another series, which really can be interpreted as a subset of that original series. And then, since we are on the topic, what is the data type of that first thing that I indexed with? If I use a single value as my index, I just get back the numeric type of the column. And since that column was float 64, floating point number 64 bits wide, then that's the data type that I get. What is your concern about these weird data types since you're not computer scientists? What do they mean to you? Well, your takeaway should be that FLOAT64 means a floating point number. In other words, it can hold decimal places. And the INT32 that we saw before, which I think we had somewhere else up here, INT32 means it is an integer type that cannot have decimal places. Both of those support mathematical operations. INT and FLOAT, int and float, support math operations. If you see object as your data type, and remember that it's abbreviated to D type here, that's just short for data type. If you see object, that means it's a string or a very, very generic type that does not support all the operations that an arithmetic type would support. So your takeaway is just be able to differentiate between the math types and the non-math types. And then within the math types, notice which ones have decimal places and which ones do not. Back to the slides. The next thing we'll look at is how to take a series and make it into a data frame. The concept of a data frame is one or more appended series objects. Each series is a column, and as we append columns together, we get a data frame. The index persists if there was one, or you could conceivably discard the index if you're doing certain operations where you don't care about the index anymore. In this example, we're going to take two series objects, myData and myData1. I'm not feeling too imaginative with my names today, it looks like. We're going to convert myData and myData1 into series objects, mySeries and mySeries1. And then we're going to concatenate them together into a data frame. Now, they both have the same index. Be very careful about that. This one is easy because they both have the same index. If the indexes were different, you might not get the results you're hoping for, and I'm not going to go too deeply into that because this is an intro course. But be acutely aware of that the indexes match. When I print that out, it's starting to look like a spreadsheet now because I have my custom index over on the left, IBM, P&G, Microsoft, Home Depot. I have two columns, stock price and market cap, and you can see the pattern. I would just continue adding columns to that data frame. The Concat method provided by Pandas lets me provide an iterable list. In this case, I'm providing a list, and inside that list are series objects, series data types. And axis 1 means concatenate along the column axis. So this is a little cookbook example of how to take two identically formatted series objects and put them into a data frame. Let's take this code back and talk about it in Jupyter Lab. We're building a nice little notebook. Again, point out the fact that each series has the same index. So I've gotten redundant in that I specified that index twice when I created the first series and again when I created the second series. And that makes me itch. Whenever I see duplicated code, I start to think, can I consolidate that code? In the name of efficiency and ease of maintenance, and possibly making it run a little faster too. I am going to do that now. I'm going to take this list that appears twice and I'm going to replace it with a name. I'll make sure that you do a cut on one of these when you follow along. Don't just delete it. Cut. I don't think I can do a cut cell. I think I'm going to need to do a Control X. So you can't see me do that, but I'm highlighting the list of index values and I'm pressing Control X and I'm replacing that with a name. And I chose the name my index. I'm not done yet because as it's written now it's going to crash. There's nothing called my index yet. You can see that it says my index is not defined, and that's okay because I'm going to come back and realize the error of my ways and I'm going to create my index. Now I've consolidated two references to the same thing, so I don't have potentially twice as much space consumed in my program. It's also much easier to read. And I can make use of that later if I want to add more series to my data frame. After that modification, I'll run this and it should be the same. Looks good, looks a little bit better, more clean. Let's add another row to this. I'm sorry, another column as an exercise. And you can just follow the pattern. I'll create my data 2 and my series 2. I'm in a bit of a rut here, aren't I? My series 2. Make sure you edit the occurrence of the name of the series. I mean the NumPy array, sorry. And then I will put something in here of interest to this data. So I will say the primary focus of this company is IBM is tech, P&G is consumer, Microsoft is also tech, Home Depot is retail. Retail and consumer are probably the same thing. I just wanted something different there. I'm not done yet. I created my third series. It's called My Series 2. It needs to be added to this Concat list, My Series 2. This is still a list. The Concat function will iterate over that list, combining all three of those series elements together into one data frame. There we go. Back to the slides. The next thing we're going to do is create a data frame using a slightly different technology. We learned how to do it using a series. We're going to learn how to do it now using a dictionary. The keys will become column headings and the values will become the values in that column. Also notice in this first example that we are not specifying an overriding index, therefore we just get the numeric index starting with 0, which is okay if we don't care, but we usually want to put something in there. So in our notebook, we have this cell ready to run and it generates the expected output. We have 3 columns, guava, pears, and avocados, and 4 rows under each column, but we don't know what those rows represent because there's no index by row. It could be the number of avocados sold at a particular Kroger, or how many went bad, or how many it takes to make guacamole. I don't know. In slide 12, we realize the error of our ways. We're going to add an index, but we're going to do it after the fact. So instead of going back and modifying the dictionary, we're just going to add the index to the existing data frame. And that is the index property of that data frame. It's simply an assignment statement to some iterable Python structure, and commonly it's a list. In this case, I'm saying there are 4 rows in my data frame. I already know that. I'm going to provide 4 string values, Kroger, Publix, Remke, and IGA, and those will become the indexes for each of those 4 rows in the existing data frame. And then I can also give the index a name, because that's nice. I mean, most people would look at that and realize those are stores, but it's possible that somebody might not, and it's possible I want to draw their attention to that column, and it will allow me to give it a semantically useful name. So I'll take that code back over to my notebook. And then let's see if we can break that. You can imagine it's fairly easy to cause a problem. So there's a 4th kind of store, Giant Eagle, which is in Columbus, Ohio. Now there are 5 index values. However, there are only 4 rows. I have an extra index. You can imagine what's going to happen. Big, ugly error message. I always scroll to the bottom. The error message is always at the bottom. Length mismatch. Expected access has 4 elements. New values have 5 elements. Okay. And it tells you that it took place on the line where I'm trying to define that index for my existing data frame. So during the execution of that line of code, the number of index values on the right inside the list don't match the number of rows in the data frame on the left, and boom, you have a problem. Can't continue. We'll just take that out. Then on the second line, I'm adding the index name. Once I correct the error that I just introduced, I can run it again. The store label shows up as the name of the index. It's kind of tucked in there at the top of the column where the indexes are. It can't be mistaken for a column heading. The column headings are offset a little bit from the index name. Now, I don't know if this works because I'm just out of the habit of doing it. Can I just type df here? Yeah. A lot of you do this, and that's fine. I'm just out of the habit. If you just type df as its own standalone statement in a cell, if that's a data frame, you get a nicely formatted result with some shading and some lines dividing things. And that's fine. I'm just not used to it. Let me try something else. I seem to have noticed a bit of a weirdness. I'm going to put another print statement here just for no good reason. Below that df line where I just referenced df all by itself and it printed out that nicely formatted data frame, I'm going to put a print statement right below that df. And you'll notice that you don't get the data frame anymore. You don't get that nicely formatted contents of your data frame. And if I remove this hello print statement, then it comes back. And what I've learned then, I think it's true, is that these references to variables without the context of a print function, they only seem to work at the bottom of a cell. And I don't think it's a bug, but it's, I guess you could call it a feature. It's just weird. So I don't, that's why I don't do it, is because I'll always find myself putting some more lines in that cell, and then that little reference to that variable doesn't generate any output anymore, which is confusing. So you're just going to see me use a print statement all the time. You're not going to see me fall back on just referencing the variable name. I think it works for a series too. If you go back up, let's go back up a couple of cells, way back up a couple of cells to the very third cell. When I create my first series, which we did like 20 minutes ago, if I just reference my series as the last line in that cell, it will dump out the series. There you go. But it doesn't look like it's any better formatted than using the print statement. Just my background as a programmer, referencing a variable name kind of out of context, just there on its own line of code without a print statement wrapped around it, just looks odd. I just don't have a habit of doing that. But if you do, that's fine. Back down to the bottom of our notebook, and we'll just continue on with our discussion. On slide 13, we've realized that our data frame is nice, but it needs more rows. Two stores have come into existence. We found out there's a Thriftway and a Meijer in the neighborhood. Thriftway was in town for Cincinnati for a long time. They're not anymore. They were struggling, and they were purchased by a chain down south. I don't even remember the name of it. Was it Publix? I don't remember. But anyway, there was a chain down south that purchased all the Thriftway stores. And if things were okay for a while, they kept the Thriftway name and people still went in the store. But we noticed that a lot of southern brands began appearing in Thriftways in Cincinnati, Ohio. Brands that had names that referenced the South and the southern United States, which just looked weird in Cincinnati. And eventually, I don't think that was the root cause, but eventually Kroger bought the Thriftways, closed a lot of them, turned some of them into Kroger. So if you see Thriftway, that's just a callback to a brand from the old days. In this example, which has nothing to do with the history of Thriftway, we are creating two rows. The rows are in the value of those key value pairs in the dictionary. And then the columns are the keys in those key value pairs. So the columns have to match what's already there in the data frame, else we have a problem. Take a close look at my code. We had guavas, pears, and avocados in all of our previous examples. We still do in this new data frame, and then we're adding two more rows. So we create the dictionary. We use the dictionary to create a data frame. The data frames don't know anything about each other yet. We add an index to this new data frame because we learned there are two more stores in the area. Those need to be rows, row indexes for those two stores. We changed the index name to store to match what was already there, what is already there in our existing data frame. And then finally, after all that hard work configuring a new data frame, we use the append function to take our new data frame and tack it onto our existing data frame. All of this code would love to travel back to Jupyter Lab with us. Brand new cell, run that baby, and it crashed. You were probably all screaming at your monitors, fix the quotes, fix the quotes. I think there's only one quote that was out of place there. at the end of the index name store. Fix the one quote. Let's try it now. Yay, it worked. And we added 2 rows. And we created some problems, which is good. We can talk about that. We added Thriftway and Meyer. We included the indexes for Thriftway and Meyer. But we made a mistake, and it didn't crash this time, because in our new dictionary that we used to build our new data frame, we put an S on guava. That doesn't match what's on the slide, so I'll fix it in just a second, and let's make it go away. But it's a good talking point. Look what happens when you add 2 rows to a data frame and the columns don't match. It created a column called guavas, plural, and it filled in the missing data with NaN, which stands for not a number. In other words, that's Python's way of saying you didn't give me anything. If it put a number in there, then you might mistake that as a valid quantity, but NaN is not going to be mistaken for a valid quantity. Something else subtle happened too. In the first column, guava, singular, NaN was necessary to provide the missing values for Thriftway and Meyer. NaN is a floating point type. Therefore, all of the values in that column had to be converted to floating point to accommodate. And look at the second and third columns, pears and avocados. Those were fine. There were no missing values. Those are still integers. And then look at guavas, plural, at the end. And those have a lot of missing values. And they are populated with NaNs, which required everything in that column to be converted to a floating point number. So while Python is wonderfully accommodating and will provide not a number values for missing data, it also changes the data types of anything else in that column. Now, I don't like this because it wasn't really what we were trying to illustrate. So I'm going to take the S out. In the dictionary, at the very top of that cell, I'll change that back to guava. It's no longer plural. Think about what we're going to do now. When we run this cell, we already have the 2 new rows in our data frame. And this is a weird thing about Anaconda, about JupyterLab, and you just have to get used to it. There's a huge burden on you as a programmer to keep track of what you've already done as far as running cells and what's in your variables. I mean, while it's tremendously flexible and you can run the cells in any order, you can run them out of order, you can skip cells, the burden on you then is to remember that you already ran this cell once and you've already changed the contents of DF, your data frame. Your DF data frame has those 2 rows in it, Thriftway and Meyer. They're already there. This logic is going to try to add them again, but it's going to try to put in a column called guava or match it if it's already there. But pears and avocados are already there, and Thriftway and Meyer are already there. Running this cell again will be very interesting. Will it add 2 more rows called Thriftway and Meyer? Will it duplicate indices? Will it update the existing guava column with 10 and 20? Will it try to add new columns for pears and avocados, even though they're already there? Let's find out together. I can't wait. Very interesting. It added 2 new rows, and it duplicated the indices, and it put in NaN for guavas, the plural, because it no longer had those. And if I run this cell a third time, you can imagine it's going to add 2 more rows with the same index. One thing that we should probably touch on is the use of the term index, because a lot of information systems, information technology people hear the term index and they think unique. Well, in a data frame, an index does not have to be unique. You can see that I have thriftway as an index 3 times, and it lets me get away with it. So I can do that. Now, what if I try to print print? I'm in a new cell now. I'm just going to print df sub thriftway. I get an error, key error. That's because it's looking for a column. But if I do a df.loc, then I get all 3 of those thriftway rows. That means that data frames are more than happy to maintain duplicate indices. If you try to relate this to SQL Server, that's correct. You can have duplicate values in a table index, or you can specify that that table index is unique. You can go either way. I'm just showing you that here by default, if you don't do anything, you can have duplicate index values in a data frame. We're off track now, though. We've got a big mess brewing here. So what I'm going to do is first take out this print statement that I just threw in as a discussion point. I'm just going to delete the cell entirely. And I'm going to run this whole thing again, run the entire notebook, just to get data frames and all my values reset to where they need to be. That'll allow us to continue on with the slideshow. And I'll do that here. I think I'm okay now. I have guava, singular. I have pears, avocados, and I have no missing data. I think I'm back in sync with the slides again. Let's go peek at the slides and try to catch up with ourselves. We added 2 rows to the data frame. Now we've realized that we're tracking more than just guavas, pears, and avocados. And if you look at the slide now, the guavas has magically become plural. But we'll be okay with that. Now we're going to add columns. So we saw how to add rows. Now we're going to see how to add columns. And we're using indexing. So the index in those square brackets is taken to be a column name. But think about how we manipulated dictionaries a couple weeks ago. If the key doesn't exist, it simply adds that key and the associated values to the data frame. You don't have to do anything else. So this is very neat code that definitely should go back to our notebook. The first thing we do is create 2 values in a dictionary. The key value pairs, the keys are apples and melons, and the values are numeric. And then we drop into a loop, and we're going to iterate over all the elements in the dictionary. This iterator syntax is very convenient because each pass through that loop we have the key and the associated value for the next element in that dictionary. Adding to that data frame is so easy as long as everything matches, as long as the number of initializers in the value part of that dictionary entry is the same as the number of rows in my data frame. I have no worries. Then finally, when I'm done, I print it out because that makes me happy. There we go. We've added apples and melons. and we have 6 stores. Once again, making sure that the dimensions match makes this go very, very easily. Let's go back to the slides. Slide 15. Let's talk about how to extract some data from the data frame. Things that we commonly want to know. We often want to know the maximum value of something. Python has anticipated our need. Python loves us and wants to serve us. We can call the max function to get the maximum value in each column, or we can call the column name, column index if you will, and then the max function to drill down to the value in a particular column. Moderately interesting, yes, but we really don't know what row it's associated with, and we're going to get there in a second. So easy to do, but probably not going to do us a lot of good unless we have a very, very small data frame and we know what all the columns are by heart. I'm sorry, all the rows by heart. Because if I told you the maximum value of melons was 60, your next question would be, which row is that? Which store is that? And we're probably going to want to know that. So just to be complete, let's take this code back to our notebook, paste it in. If we type in a column name that doesn't exist, instead of df.apples.max, how about just df.apple.max? That's going to break, right? There you go. Data frame object has no attribute apple. Pretty good error message. I probably spelled something wrong. And that's apples. Fair enough. On the slide then, slide 16, as I said, providing the maximum value in a column is great, but we probably want to know more about that. So we can use the max function as an index, or to build an index of true-false values. And then we can use those indexes of true-false values to print rows. And this is just, to me, mind-blowing. It's so elegant. I just want to talk about it. So we'll go back to Jupyter Lab again and reproduce this amazing code. The first line, before we even get to the second line, let's talk about the first line. The first line, I commented out the second line. All we get is a column of false and true values. And since it thinks we want to know, it also gives us the indexes, which are moderately helpful there. Look at the data type here. The data type is bool, B-O-O-L, which stands for Boolean, which is a data type that can only be true or false. It can't be anything else. Again, Pandas accommodated the data in the column when it chose the data type. Since only trues and falses appear in that column, it made that data type bool. Now those values don't have a lot of interest to us in and of themselves. They're just falses and trues, and they are associated very tightly with rows. Well, so what if we use those values as flags or instructions as to which rows we really want? I'm going to uncomment that second line and comment out the first line just to keep the clutter down. And focus on what's going on inside those brackets. So inside the brackets, and those are indexing brackets, not list brackets. Inside those indexing brackets is the same thing we had on the previous line. So it's a whole bunch of falses and trues. And Pandas takes those as instructions to whether or not to print the corresponding row. If you see Kroger says false, don't print that row. Publix false, don't print that row. Down to the bottom, Meyer true, print that row. The upshot then is it's going to print the entire row where the value of apples is at the max. The entire row where the value of apples is at the max. And you just get Meyer. Pretty slick. I'll give y'all a moment to catch your breath. And I'll scroll back up and just review what's in that data frame. You can see that the maximum value of apples is in the Meyer row. With one line of code then, we're able to extract the row with the highest number in that column. What if two rows have the same max value? In our case, what if two rows had a 6 in apples? We can do that. We can simulate that by going way back up at the top of the notebook and changing one of the apples rows to 6. That's probably all the way at the top, near the top. I'm looking for apples. There he is. There's where we added apples. That's cell something. I hope you can find it. Anyway, we demonstrated how to add 2 more columns to the data frame. And I'm going to change the first row in that column to 6, just to show you that if 2 rows have the max value, it will still retrieve both of those rows. Now to make this work, I'm going to have to rerun the entire notebook to pick up all the other changes that we've made. But if you scroll to the bottom again and just review, when we run this print statement where we're looking for the max value, it's going to give us 2 rows instead of 1. It's going to give us Kroger and Meyer because they both have 6 apples. Hit the Run All button, restart the kernel, hold your breath. So exciting. There it is. Kroger and Meyer, they both have 6 apples. One line of code did that. Very impressive. Review the slides again. Let's see. Slide 17. Oh, we did that. Okay. No, we didn't. No, we didn't. Sorry. In slide 17, we are happy with what we had, although we'd like a little bit less data. It's just too overwhelming. So I can index on just the index. I don't want all the columns. I just want the name of the index. And of course that's going to print out, in our case, Kroger and Meyer instead of all the other values in the columns. So if the question was what stores have sold the most apples, if you just wanted the store names, you could have this syntax to get Kroger and Meyer and nothing else. And let's do that because it's so cool. There we go. The first one, the first print statement gives us a list of the entire list of stores that meet the criteria. The second one only prints out Kroger because we only ask for 0. So what if I ask for colon? There I go. I got both of them there. What if I ask for 1? I got Meyer there. So I can play games with that to get all the stores that showed up in that computation. Okay. Slide 18. In slide 18, this is me being curious about data types again. I'll draw your attention to my use of the type function. I just took what we did on the previous slide and I Instead of printing it out, I passed it to the type function. Then I printed out what the type function gave me. I can see that there is a thing called an index. So the data type of this expression that we were so amazed by is called an index, a new data type for us. And then the data type of the index type with a index appended to it, so indexing on an index type, gave me a string. Concern for us, not really, a bit too wonky, but just interesting if you have some curiosity about what's going on behind the scenes. Here's something that we care about. All this data needs to be ordered, and as you can imagine, Pandas wants to do that for us. Pandas is at our beck and call. We call a function called sort values. We tell it a column name. We're sorting by avocados. So all the rows in the data frame will be rearranged by order of the values in the avocados column. And I chose to sort in descending order by using the keyword argument ascending and setting it to false. Then I only ask for the top 5. So in case I had volumes and volumes of data, I could only see the top 5 there. And let's take that back over to Jupyter Lab. Run that, and remember, we still have 6 rows, but we're only seeing 5 because I only asked for 5 in that head function. And the rows are now sorted by descending order according to number of avocados. This easily breaks if we misspell avocados. And let's find out if it's case sensitive. Are the column names case sensitive? Yes, they are. Key error, avocados. If you see a key error, it's probably because you tried to do a lookup of a column name or an index name and you spelled it wrong or you did not respect case. In our situation, we lowercased the column names, and that should work. There it goes. Slide 20, here's an example of what I just did. I misspelled avocados to demonstrate a key error, and then on the slide I just completely picked a column that did not exist, and then I got the key error. That's just a visual reminder to you that you have to go back and fix something. Not a logic error, more like a data error. It only appears when you run the code. There's no way to know otherwise. So you can't check that with a syntax checker, can you? If we just want a particular column of the data frame, I can use a keyword argument columns, provide an iterable data structure, in this case a list of the columns that I would like to have. In this example, we're actually creating a brand new data frame using just the pairs column. So it's kind of a slice by column, and the original data frame is unaffected, but the new data frame just has the pairs column in it. So let's talk about that. Runs fine. Oh, doesn't run fine because the quotes are wrong. Now it runs fine. Still have my index, just have the pairs column, and now I have 2 data frames. They are not the same. One of them is much smaller than the other. They share an index. My second example that I commented out is different in that it does not create a new data frame. It just slices one column out of our existing DF data frames. So what does that look like? And quote problem again, sorry. Also comment this, left out my comment delimiter. Now I'm good. There we go. Doesn't quite look the same because it's a series, but it still gives us that column of information. Back to the slides. Thanks for sticking with me. In just a few lines of code, we can extract quite a bit of meaningful statistical data from our data frame. And it's only meaningful if you know how to apply it. I was being facetious there. So if I call describe, I can drill down into that and get values from individual columns and individual rows of what describe has given me. And this is something that I run into once in a while. I have access to this really amazing function called describe, and I have it in the Jupyter Lab cell here. But when I call describe, it gives me just this big jumble of stuff. And I'm going to comment out these other two print statements. And it's nice to look at, but if I want to do data manipulation on any of these items, I have to drill down to them somehow and get them into a variable. If I want to know the mean value of the guava column, I mean, right now all I can do is look at it on a screen and say, okay, it's 9. Thank you very much. But if I want to store it or transmit it or use it in a computation, I need to be able to drill down. And that last print statement there, and I'm just juggling around my comments here, the last print statement where I print df.describe index guavas index mean, whoops, quotes again? Is it guava? I'm sorry. It's not guavas, is it? It's just guava. There he is. So that's a 9. That's useful to me. I can do something with that. It's not buried in a huge data frame of numbers. And just to show you, let's get it. My mean, or let's just say guava mean. Guava mean equals, take off the print logic, and I spelled guava wrong. Guava mean, and then let's print guava mean equals plus str mean, because it is a number, therefore I'm going to have to convert it to a string in order to concatenate it to this other string. And I get, oh, I spelled it wrong again. Sorry, getting ahead of myself. That's better. There. So I have an individual number that I can do something with. And I can also check the type of it. Hopefully you know, or you have some idea what this type is already. What is the type of guava mean? Stop and think about that. I've extracted it from the output of the describe statement. And since it's a numeric value with decimal places, we would hope that it is a float. If it's a string, we're going to be very disappointed. Good, float 64. And that means that all of these things provided by df.describe, the describe function of a data frame, are in reasonable formats that you can extract and use to do things. Now, should you memorize that? No. Just have in the back of your mind that it is possible to call a function and get statistical data off of the columns in a data frame, which is very powerful. One line of code. It's slow. This isn't interpreted language. If you've got 10 million rows, I don't think I would do this. However, it does work on data sets of manageable size. And that brings us to the end of our journey. Thank you very much.